In this video, we are going to solve example on trigonometric Fourier series. Here a square wave is given which has amplitude plus a and minus a, and the period of this square wave is t, and we are supposed to find out the trigonometric Fourier coefficient. So first of all, we need to write down the equation for trigonometric Fourier series. Trigonometric Fourier series is given as x of t equal to a0 plus summation n equal to 1 to infinity an cos of n omega t plus summation n equal to 1 to infinity bn sin of n omega t. So before finding out the coefficients a0, an, bn, we need to mention the period of this signal. So here period for this signal is represented as capital T. So here we have period of the signal as capital T. Now we need to find out the coefficients. So let us start with the first coefficient to find first coefficient, which is a0. So we have the formula for a0 as 1 by t integration 0 to t x of t dt. So we are going to put the values of x of t in this equation, and then we are going to evaluate the integration for a single period, that is 0 to t. So here we have period as t, so this t will be as it is. Now the integration is going to split up because in the given equation this square wave has amplitude a from 0 to t by 2. So this coordinate is t by 2, it is half cycle, and from t by 2 to t it is minus a. So let us substitute this values in the integration. So integration from 0 to t by 2, value is a into dt, plus integration from t by 2 to t, value is minus a into dt. So if we simplify this equation, we have 1 by t, then a can be taken common. So from both the integrations, a into integration of 0 to t by 2 dt plus a into t by 2 to t dt. But here we have the sign as negative, so this plus sign now becomes negative, it is minus a. So we have 1 by t. So again from both the integrations we can take a common, so we can take a out of the bracket. So here becomes, so integration of dt is t with the limit 0 to t by 2 minus integration of t is dt is again t with the limits t by 2 to t. So if we simplify it now, a by t, here the upper limit is t by 2 minus 0, minus sign as it is. Now upper limit is t minus lower limit is t by 2. So if we simplify it further, we get a by t, t by 2 minus t, this minus and this minus becomes plus t by 2. So here we get the answer as t by 2 minus t plus t by 2. So it becomes 0. So our answer is 0. So the first coefficient a0 is 0 for the given example. Now let us find the second coefficient to find an. So for an the equation is given as an is equal to 2 by t integration from 0 to t x of t into cos of n omega t dt. So again substitute the values. So it is 2 by t. Here the integration is again split up into two parts, 0 to t by 2, for which x of t is a cos of n omega t plus integration from 0, it is not 0 now, it is from t by 2 to t, x of t is minus a cos of n omega t dt. So let us simplify it further now. A can be taken out of integration, so integration remains 0 to t by 2 cos of n omega t dt. Now here we can take minus a common out of the integration, so t by 2 to t cos of n omega t dt. So now if we look at the equation, we can take a common. So we have 2a upon t. In the first bracket, it is simply integration from 0 to t by 2 cos of n omega t dt minus integration from t by 2 to t cos of n omega t dt. So if we integrate this equation now, we get 2a upon t as it is. Integration of cos is sin n omega t divided by n omega. With the limits 0 to t by 2 minus, so again for second term it is cos, so it is sin of n omega t upon n omega with the limits t by 2 to t. So let us simplify this now. So we have 2a upon t. So in both the brackets we have at denominator n omega, so let us take it out of the bracket so that we can simplify our equation. So upper limit is t by 2, so sin of n omega t by 2 minus sin of 0. This is the first bracket, minus in second term we have sin of n omega t minus sin of n omega t by 2. So if we simplify this equation, so here we have 2a upon n omega t, and now if you look at this bracket, first term is sin of n omega t by 2 minus sin 0 is 0 minus sin of n omega t minus minus becomes plus sin of n omega t by 2. So now here we get the equation as 2a upon n omega t 2 sin of n omega t by 2 minus sin of n omega t. But now we know that this omega can be represented as 2 pi f, which is nothing but 2 pi by t. So for given signal, capital T is the period, so frequency is inverse of time, so it is represented as 2 pi by t. So just replace this value in this equation. So here we have 2a upon n into 2 pi by t into t, 2 sin of n 2 pi by t into t by 2 minus sin of n into 2 pi by t into t. So here 2 gets cancelled out. Here this t also gets cancelled out. So here the term remaining is simply a upon n pi, and in the bracket here we have 2 sine of, here also now the terms 2 gets cancelled out, t also gets cancelled out, so sine of the remaining term is only n pi minus sine of, so if we simplify these terms again, so n, this t and t gets cancelled out, so here it is simply sine of 2n pi. Okay. So now here we have the equations or the angles of sine as n pi. We know that we have one more standard results, that sine of n pi is always 0. Therefore the coefficient an will be equal to a upon n pi, 2 sine of n pi, sine of n pi is 0, so this first term becomes 0, sine of 2n pi is also 0, so it becomes 0, so an coefficient is equal to 0. So we have obtained the second coefficient an, which is equal to 0. Now let us find the third coefficient bn. So we know that bn is given as 2 by t integration from 0 to t x of t into sine of n omega t dt. So again replace the value of x of t in this equation, so 2 by t as it is. So here in the first part we are going to split up the integration 0 to t by 2 a into sine of n omega t dt plus integration from t by 2 to t minus a into sine of n omega t dt. So again simplify it the way we have done it for the an coefficient. So we have 2 by t from both the brackets we can take a common, so it becomes 2a by t. In this we have integration 0 to t by 2 sine of n omega t dt minus integration from t by 2 to t sine of n omega t dt. So we know that integration of sine is minus cos, so 2a by t. So first we have minus cos of n omega t divided by n omega with the limits 0 to t by 2 minus, for the second integration, so it is again minus cos of n omega t upon n omega with the limits t by 2 to t. So here n omega is at denominator, in both the terms we can take it as common, so here we have 2a upon n omega t, and now apply upper limit minus lower limits. So here first term is minus cos of n omega t by 2 minus, so now minus of minus cos becomes plus cos of 0 minus, so in the second term we have minus cos of n omega upper limit is t minus, just write it below, minus of, so again it is minus, so minus minus becomes plus cos of n omega t by 2. So this completes our upper limit minus lower limit. So let us simplify it further now. So here we have 2a upon n omega t, so minus cos of n omega t by 2 plus cos 0 is 1, so minus minus becomes plus cos of n omega t minus cos of n omega t by 2. So now if we simplify it further, we get 2a upon n omega t. So 1, we'll just rearrange the terms, 1 plus cos of n omega t minus, so minus cos of n omega t by 2 minus cos of n omega t by 2 becomes 2 cos of n omega t by 2. Now again substitute the value of omega. So we have omega equal to 2 pi f, which is equal to 2 pi by t. So if we substitute these values, so here it becomes 2a upon n 2 pi by t into t 1 plus cos of n 2 pi by t into t minus 2 cos of n 2 pi by t into t by 2. So now if we simplify this equation, so here 2 gets cancelled out, t also gets cancelled out. So in the cos of n 2 pi by t, here also t gets cancelled out, and in the third equation 2 and t gets cancelled each other. So the simplified equation becomes a upon n pi 1 plus cos of 2n pi minus 2 cos of n pi. So now again we have one more identity. Cos of n pi is equal to minus 1 raised to n. Now in our equation we have cos of 2n pi. So cos of 2n pi will be equal to minus 1 raised to 2n, which is equal to 1. So let us substitute these values in the above equation. So we get bn equal to a upon n pi 1 plus cos of 2n pi is 1 minus 2 cos of n pi is now minus 1 raised to n. Okay. So this becomes a upon n pi 2 minus 2 minus 1 raised to n. So this is the bn coefficient. Now if we look at this equation carefully, here it is 2 minus 2 into minus 1 raised to n. So we can represent this bn as, so if the value of n is even, if the value of n is even, so minus 1 raised to 2, so minus 1 raised to 2 is 1, and therefore 2 minus 2 becomes 0. So bn value becomes 0 for n equal to even values. And if we substitute value of this n as odd, so minus 1 raised to 3 becomes minus 1, so 2 minus of minus 2 becomes plus 2, so 2 plus 2 becomes 4. Therefore for values of n equal to odd, we get the answer as 2 plus 2 becomes 4, so 4a upon n pi. So this is the final value of coefficient bn. So now we have obtained all the three coefficients. So we need to represent the final answer as in terms of x of t. So we know that x of t is equal to a0. So a0 is 0 plus summation n equal to 1 to infinity an cos an is 0 plus summation n equal to 1 to infinity bn, but our bn is now 4a upon n pi sine of n omega t. But here this bn is 4a by n pi only for values of n equal to odd. So our final answer becomes x of t equal to summation n equal to odd only for odd values of n, and that n starts from 1 and goes to infinity. So from the range 1 to infinity we are only supposed to take odd values, and the coefficient is 4a upon n pi sine of n omega t. So if we look at this equation states that if we have a square wave, and if we represent this square wave in terms of Fourier series coefficient, so this square wave is summation of only odd harmonics of sine wave. So for square wave it is summation of odd harmonics of sine wave, which is given by this equation. So if we look at this equation, so summation of n equal to odd, 4a upon n pi is the coefficient, that is amplitude of this sine wave, and only this sine wave exists for odd values of n. Therefore we can say that square wave is summation of odd harmonics of sine wave. Now we need to plot magnitude and phase spectrum. So to plot magnitude and phase spectrum, first of all we'll just represent this x of t in expanded form. Okay, so x of t is given as n equal to odd. So let us start with the odd values. So let's say n equal to 1. So for n equal to 1 we have 4a upon n is 1 by pi into sine of n is 1, so it becomes omega t, plus, so n equal to next odd number is 3. So 4a upon 3 pi sine of 3 omega t, plus next odd value is 5. So 4a upon 5 pi sine of 5 omega t, plus, and so on up to infinity. So in order to plot amplitude spectrum, so we have under root of an square plus bn square. So but in our case we do not have an value, so it is under root of bn square, which is nothing but equal to bn. Okay, so our bn value is 4a upon n pi only for n equal to odd. So let us plot it. This will be our n origin, and mod of an, that is what the magnitude spectrum. Here it is capital A, it is just a representation of amplitude spectrum. So now here if we look at the values of n, only at values of n equal to odd, so 1, 3, 5, 7 and so on, these values will exist. So for n equal to 1 we have 4a upon n pi, and n is 1, so we get a signal of amplitude 4a by pi. Similarly at n equal to 3 we will get somewhat lower amplitude, its amplitude will be 4a upon 3 pi. For 5 there will be somewhat lower than it, so 4a upon 5 pi. For 7 there will be again lower amplitude, it will be 4a upon 7 pi, and so on. So in this way we can plot the magnitude spectrum of the Fourier series. Similarly, we need to plot phase spectrum. So for phase spectrum, we have tan inverse of, so let's say phi of n bn upon an. So in our case, this bn exists and an is 0. So we have 0 value for tan inverse. Therefore, we only need to draw an axis, and at odd values we need to show it with 0 magnitude. So here this axis are n, and here it is phi of n, or we can represent it as angle also. So let's say phi of n. So in this way we can find out amplitude spectrum and phase spectrum in case of Fourier series. Remember here, whenever we are plotting amplitude and phase spectrum of Fourier series, it will be always in the discrete form, because we have only the values of n at discrete integers. So if we look at this example, it was given with a square wave. This square wave was having amplitude an minus a, and the cycle was from 0 to t. So we have obtained a0, which is 0. Then we have obtained an, which is again 0, and then we have obtained bn, which was Fourier upon n pi for odd values of n and 0 for even values of n. And then we have represented this equation in terms of the original equation of trigonometric Fourier series, x of t equal to a0 plus summation n equal to 1 to infinity an cos, so an is 0, plus summation n equal to 1 to infinity bn sin. So but for bn it exists only for odd values, so we have written it as n equal to odd, and then the final answer was represented in x of t form. So remember here, in Fourier series, a given signal is in time domain, and representation of Fourier series is also in time domain. And then we have obtained magnitude, that is amplitude and phase spectrum, using the equations. For amplitude it is under root of an square plus bn square, and for phase it is tan inverse of bn by an. So with this it completes the numerical on trigonometric Fourier series.